This is the start of a brand new section. It's called Rational Functions and corresponds to section 5.6 of the textbook. So we're going to have a little bit of text here, so bear with me, and then we'll get into an example. A rational function is any function of the form p of x over q of x, where p and q are polynomial functions. And here are a few examples of rational functions. F of x equals x plus 1 over x minus 3. F of x equals x squared minus 3x plus 1 over x cubed minus 1. And f of x equals 1 over x. So rational function's a new kind of function for us. We're familiar with polynomials that we see in the numerator and denominators, but now we're dividing these polynomials and creating a new kind of function. Domains of rational functions. We have seen that the domain of any polynomial function is all real numbers, the interval from negative infinity to infinity. That's one reason why we like polynomial functions. Their domains are always very straightforward. There's nothing to figure out, really. In contrast, rational functions often have domains that are not minus infinity to infinity, that are not all real numbers. A rational function is not defined at any value of x that makes the denominator equal to 0. These are the only values of x not included in the domain. Thus, the domain of a rational function consists of all real numbers except those numbers that make the domain equal to 0. So in these examples, for this first example, we would say the domain consists of all real numbers except 3, right? Because 3 makes the denominator 0. For the second example, the only number that makes that denominator equal to 0 is 1. So the domain consists of all real numbers except x equals 1. And in the third example, the domain is all real numbers except x equals 0. Now we're going to primarily be interested in graphing. Our goal is to be able to graph rational functions by hand. First, we'll look at two examples in detail and plot a lot of points. Next, we'll set up a step-by-step process for drawing a graph based on important characteristics of the function without having to plot lots of points. From then on, we're going to rely on the step-by-step process. Still, it's always okay to plot some points if that helps you figure out what the graph is. So we're going to start out with a couple examples in detail, and then we're going to develop a process. But I don't want to give you the process until we work through these couple examples. And the most natural example to look at, first of all, is just the function 1 over x. So if you're familiar with this example, if you just know it inside and out, maybe you can bypass this video, but because we are going to talk about this in quite a bit of detail. And I already set up a graph grid, and I set up some tables to save us a little bit of time writing information down. But even if you are familiar with this graph, there's going to be some notation here that I think will be brand new to you. Okay, so this is, and I think of this as the simplest possible rational function. So it's sort of a great place to begin. And I'm just going to plot some points and compute some values. Now I set up a table here of values on the left side. Instead of doing the negatives first, let's just go down to the positives. And the first thing I want to notice here is where 0, x equals 0 is in my chart. The function is undefined at 0. So there is no point to plot, right? We can't calculate 1 over 0. When x is equal to 1, 1 over 1 is just 1. Add a half. When x is 2, we get a half. When x is 3, we get a third. When x is 4, a fourth. So we keep getting these fractions. At 10, when x is 10, we get the function value 1/10. And at 100, we won't be able to plot this on my graph, but we're going to get the value 100. Now let's just go down here and plot some of these on my graph grid. I guess we can So at 0, there's nothing to plot. At 1, I already set up a scale, by the way. So just each square is worth 1 unit in this graph. So we got the point 1, 1. We got the point 2, 1/2, 3, a third. So I just sort of approximate that location, right? 4, a quarter. And I think you can see these points are dropping down closer and closer to the x-axis. And at 10, we're going to go into, I can't really even plot that. All I can do here is try to show that I'm going to get closer and closer to this x-axis as I move to the right, right? Okay, now let's look at some negative values. Maybe I'll come up from below at 0. 1 over negative 1 is negative 1. 1 over negative 2 is negative a half. Then I get negative a third, negative a fourth, right? 1 over negative 10 at negative at 1/10, negative 1/100th at 100. So it's kind of similar to what happened with positive numbers, but I'm getting negative y values for all these negative x values. So on my graph, at negative 1, I actually have y value negative 1. At negative 2, negative a half. At negative 3, negative a third. Negative 4, negative a fourth. So I'm getting closer and closer to that x-axis as I move to the left, but I'm below the x-axis. At negative 10, I have negative 1/10. That would barely show up on this scale as separate from the x-axis. And so my graph's going off to the left here. Now, I think you can see that when x is very, very large, like 100, I'm even closer to the x-axis. And when x is very, very negative, like negative 100, I'm closer to the x-axis. We can go ahead and analyze the end behavior already of this function. And we're going to use that same notation we used with polynomial functions. We can say as x approaches infinity for this function. Now we won't say, we will say f of x arrow, f of x approaches. Now this is different from polynomials because we're not approaching infinity or minus infinity, we're approaching the x-axis. And the x-axis is points with y-coordinate 0. So the f of x values are approaching 0. Remember, f of x just means y, and this is an aspect of our end behavior. Now we also can talk about what happens as x approaches minus infinity. And in that case, the function values or the y values, even though they're negative, they're getting closer and closer to 0. So they're approaching 0. So this is the other end behavior. And now we got to think about what in the world is going on here in the middle of the graph around the y-axis. I can't plot a point when x is equal to 0, right? And that's why I have some more values here on my table that I'm going to plug in. Now remember, at 0 we're undefined. And maybe, again, I'll start with these positives first. So, 1 over 0.5 at 1/2. So that's 1 over 5/10 is 10/5 or 2. So at 0.5, we're 2 units up on that graph. 1 over 0.2 is 1 over 2/10, which is 10/2 or 5. Now, it's hard for me to hit 0.2. I'm just approximating. It's closer to the y-axis, and then I have to go all the way up here 5 units, right? And 1 over 0.1, that's 1 over 1/10, is going to be 10 over 1 or 10. So by the time I'm at 1/10, very, very close to the y-axis. I'm shooting all the way up here. And so what's happening to this graph is it's like kind of rounding the corner and taking off for space, shooting upward. And then I put in here 0.001. Let's see, that's 1,000th, 1 over 1,000th, if you figure that, that's going to be 1,000. So as I get closer to 0 on the x-axis, my y values are getting huge, right? And now what about the negative direction? If I take 1 over negative 0.5, it's similar to what's happening with a positive, but I'm going to get a negative value, right? Negative 2. And 1 over negative 0.2, I'm going to get negative 5. So let's see, at negative 0.5, I'm at negative 2. At negative 0.2, which I can just sort of estimate, I'm already down at negative 5. At negative 0.1, I'm going to get negative 10, comparing to what we already got with a positive. And at negative 0.0001, I'm going to get negative 1,000, way the heck down here. So what's happening is here, we're just plunging downward on this side, right? So this graph never touches the x-axis, never touches the y-axis, and there we got our graph. But now I want to add a little bit more notation. What I was doing up at the top, on this second table, or the table on the right, I was looking at the behavior of the function near x equals 0. And when we look near x equals 0, we're going to use a special kind of notation. So we looked at values, I'm going to draw an arrow here, getting closer to 0 when they were positive, right? When we were to the right of 0. There's a special notation for that. We're going to write x arrow 0 with a little plus sign. The little plus sign doesn't mean positive so much as it means numbers to the right of 0, greater than 0. And then up above, I'm going to draw an arrow coming down here. We looked at values approaching 0, x values approaching 0, but from numbers smaller than 0, right, to the left of 0. And I'm drawing a distinction here because we have two very different things happening. Let's copy that onto the graph here. I'm going to say as x approaches 0 from the right, f of x, the y values, blow up. So the y values increase without bound, so we say they approach infinity. And I just want to, I'm going to write out the words for how we read this notation because I think that's probably new for most of you. As x approaches 0, so as x approaches 0, the way we read the little plus sign is we say from the right, and we mean from the right of 0, from the right-hand side of 0. So from this side. So this is the formal notation that represents the behavior of this graph shooting up to the right of the y-axis. On the other side, here we would say as x approaches 0, from this negative direction, from the left is 0, I write a minus sign, and then we say f of x approaches, of course, minus infinity here. So there's a difference. We have to distinguish these two different sides. And again, I'm going to write the words for this. X approaches 0 from the left, and from the left of 0 is, we don't always say of 0, we just say from the left, but that implies of 0. And I just want to remind you guys that these f of x's all refer to y values on the graph. Okay, and since we're just staring at the graph, I want us all to remember that we're just looking at the graph of the function 1 over x. And just two more things before we quit here now. So we have a special name for what's going on with the x and y axis here. We say the x-axis is a horizontal asymptote to the graph, and the y-axis is a vertical asymptote. So an asymptote is a line that a graph approaches, but may never actually even cross it, just gets closer and closer and closer to it. And so there it is. I think I'm going to say all I wanted to say about f of x equals 1 over x. We had a table of values, and all we did was plot points, and we have this special notation now. These four situations right here, here, the end behavior, here, here, I would say the behavior near x equals 0.